Hello all, welcome to the video lecture series for the subject operating system. Now I am going to explain you all about a dining philosopher problem, and the solution here it is made with monitors, right? So this is the only difference. The previous lecture I was explaining you about the basic principles of dining philosopher problem and how this classical synchronization techniques has been adopted. Here you can check it, the dining philosopher solution using monitors. How does the monitor works here? That is our process, right? Let's see, get into the topic directly. So here you can see that dining philosopher problem has been solved with monitors, but here you can check that the deadlock free solution has been adopted by this dining philosopher problem using monitor, right? So if any philosopher is started eating, the other philosopher has to wait, and each and every philosophers will be allocated with a synchronization technique. How does which philosopher and all the other condition has been checked here, right? The only difference with the classical synchronization dining philosopher problem and monitor is here the condition self has been introduced. Let me tell you what is this self. It is used to delay the philosopher when he is hungry. Say for example, philosopher number 0 is hungry, but this philosopher couldn't able to find the adjacent chopstick to eat. So what this self condition will do here, it is if at all this P0, that is philosopher 0, is hungry but unable to obtain the chopstick, this philosopher unable to obtain chopstick number 0 or chopstick number 1, then what this condition self will do is it will delay this philosopher, right? Whenever it is hungry, it will delay the philosopher when this chopstick, adjacent chopsticks are not available, right? Let's see how this particular procedure, the theoretical way of understanding, is practically applied, right? Okay, for example, here we are going to see that how this monitor dining philosopher works. This monitor dining philosopher works with one particular data type called as enum, right? This enum will have three variable. Number one, think. Number two is hungry. Number three is eating. So one philosopher, let me draw this simple diagram so that you will understand. So philosopher number 0, philosopher number 1 and 2 and 3, and philosopher number 4. So we know that C stands for chopstick, chopstick number 1, chopstick number 2, chopstick number 3, and chopstick number 4. So let me, so here it is only one chopstick here. So C0, these are all the chopstick. For identification I have drawn in this way. Okay, so there is no chopstick here, right? Now you can understand there is totally 5 philosophers are sitting in a dining table, and each and every philosopher will have one adjacent chopsticks. You can check that 2 adjacent chopsticks. Philosopher 1 will have 2 adjacent chopsticks. Every philosopher will have this, right? So the state here, it is how many philosophers are there? So the state here, it is 5, totally 5 philosopher, 5 chopstick. And also the condition self is also 5. That is, condition self is used, I told you already, it is to delay the philosopher when the philosopher is hungry but the philosopher couldn't find, unable to obtain the chopstick, right? So I have drawn this diagram for the self understandability of how this pickup and drop is actually working, right? Okay, let me take you to this solution part. So here I have divided this particular algorithm into 5. Number 1 is pickup, number 2 is put down, that is dropping, number 3 is to test whether this chopsticks are available or not, and number 4 is for initialization of the code one by one. Okay, let's check how this solution works. Now listen, why pick up int I? I will be initially always starts with the philosopher number 0, right? So I will be initially always 0. Now say for example state of I. State in the sense number of philosopher available in that particular round table. Now I told you I'm going to start with philosopher number 0. So here you can check it. The value of I here it is P0. So P0 is equal to hungry. I told you already, if P0 is hungry, it will check two things. One is left and right side of this philosopher should not be eating. That means C0 and C1 will be free. So it is going to test now. So state of P0 is equal to hungry. Then test I. Now which two I, that is which two philosophers should not eat. Now say for example, void test int I. I am going to check this integer value, that is argument I. If it is a long if, now double ampersand, that is a logical ampersand has been used, the condition has to be checked. If state of I plus 4 modulus 5. So we know what is I here. I is 0, 0 plus 4 modulus 5. The value you know very well, it should be 4, right? So P0 is checking whether P4 is eating or not. Check here, 4 modulus 5 not equal to eating. That means the condition is the fourth philosopher should not eat. You can check this particular thing also here. The fourth philosopher, if P0 want to eat, P4 should not be eating. So that is a condition number 1 has been checked. Ampersand, ampersand. So here you can check it. Who is hungry now? That is P0, state of 5. We already checked that here. So if this particular P4 is not eating and P1, this is P0 is hungry, and the next state, which state, say for example, we have checked P0 is not eating, and also this P0 want to check P1 should not be eating, that is both this adjacent philosopher should not eat. So let's check in this particular condition again. Ampersand, ampersand, that is logical, and state of I plus 1. What is the I is here? 0 plus 1 modulus 5. Automatically what's the answer? 1. So this P0 is eating, I mean hungry. It should find P4 and P1 is free. That is, these two philosophers should not eat. Check here. State of 0, that is I is 0 plus 1 modulus 5 not equal to eating. Who is not equal to eating? Here it is 1, here it is 4. Both these two philosopher is not eating and P0, that is philosopher number 0, is hungry. Then state of I is equal to eating. Right? So now this philosopher state of I is what? P0. Now P0 is allowed to eat. Now self of I is what? P0 dot signal. It is signaling that this P0 is eating so that the adjacent philosopher cannot eat. So that is the actual procedure here. So here the monitor is used, that is it will have 3 states. One is hungry, eating and thinking. So we have already mentioned here the dining philosopher using monitor. Now you can check it. We are going to check the same scenario, but we are using 3 arguments to check it. So that's the difference between a classical dining philosopher, and the same solution has been applied through monitors, right? Now say for example, here the process is to check adjacent philosophers are not eating. So the philosopher who is ready, that is hungry, can take the chopsticks. So this is how described here. Let's check whether the process, that is philosopher 0, want to put down the chopstick. You all know that very well because I was explained the same thing in classical dining synchronization problem, that is philosopher problem. So here void put down in int I, this is the argument I. State of I is equal to thinking. Now this P0 want to drop the chopstick and it is voluntarily inviting himself to go for thinking, because I have completed my process. I know more. I have no more process to be done here. So I want to put down the chopstick. How I need to do? See here. State of I is equal to thinking. If my state, that is P0, want to move into thinking state. Thinking state in the sense what? I have nothing to done, right? So again I am going to thinking state. So it will test. Again it will call this function test. I plus 4 modulus 5. What is I plus 4? 0 plus 4 modulus 5. The value is 4. You all know that. I plus 1 modulus 5. So 0 plus 1 modulus 5. The answer is 1. So these 2 chopsticks, that is philosopher number 1 and philosopher number 4 will be put down. right? So this two chopsticks adjacent, adjacent to this philosopher, you can check that these philosophers can able to take the chopstick now because this P0 has been put down the chopstick. So this is how this thinking process has been happening. Let's see what is this initialization code. This code is to process each and every philosophers. The first philosopher starts with 0 and the last one is 5. So approximately you can check that I should be less than or equal to 5. So totally it is 5 philosophers over here. It starts with 0. Now you can check that every state will be initially in thinking process, right? Every state will be initially processed in thinking. Each and every state will be allowed to think, hungry and eat. So one by one, it is process 0 first, again process 1 up to process number 4. So I hope this finds you well.